Okay, so one nice thing about the memory protection stuff we've been talking about is that it could be used to sort of create these fences or isolate these different applications from each other. I was talking about process A cannot access memory that currently belongs to process B. But the same mechanism actually could be used to isolate the operating system. Remember, we wanted to tamper resistance for the operating system. You shouldn't be able to alter from untrusted application code. So we can isolate the operating system from untrusted application code using the same memory protection mechanisms we're talking about. So the way we do that is we're going to say the operating system, also called the kernel, is going to reside in a portion of each process's address space. So the address space in which a process executes now has two parts, where the user code and data is going to go and where the operating system is going to go, operating system code and data. So the OS resides in, and that part of the address space is common across different processes, is going to be in a portion of the address space. So think about your address space. There's a user portion, a user area, and then there's an OS or kernel area. And this holds for each and every process that we have in the system. And remember that we talked about system calls and things like that. Whenever you want to go from the user side, user portion of the address space to the system portion of the address space, that transfer has to be special and handled by the operating system. Can only be done through the system call that we're talking about. So one way I want you to think about is that, let's say this is the address space that process A executes in. Then we said there is this fence or boundary. The OS goes here, the user code goes here. And when you are here, when you're executing in this portion, you're not allowed to access this part of the memory. Remember the execution mode that we're talking about? So the hardware is going to say if you're in the user mode and you're asking for an address here, that's not going to be allowed. Okay, so the way operating system is isolated from application code, which is untrusted, is essentially putting those in separate places and making sure when you hear, you can't go into the operating system. Well, there are these, we said the call gates or controlled entry points through which you can come in, but then we coming in by making a certain call, the operating system understands, and the operating system is going to do whatever checking it needs to do, and then you're going to be executing in the operating system while you access anything here. And when you're done, you're going to return back to the user level. So we use the same memory protection mechanisms you're talking about, page tables, the protection bits, what different page tables we have for different processes for the operating system. So remember, one of the things that I can't overemphasize is the operating system or the trusted computing base that we have has to manage these page tables, because page tables control what portions of memory you can access and in what manner. And the operating system says this is your code. You can execute it, but you can only execute, or this is your stack. You can read write it, but you can't execute from it. That's a non-executable stack and things like that. So this is how the operating system is going to actually protect itself from untrusted process codes, and also allows these untrusted processes protection from each other. So process A can't, for example, corrupt the memory of process B because the way the address translation and the protection mechanisms work.